It's time for some more Cleo Abram. Specifically, what if you just keep digging? Well, you'd break whatever it is you're digging with. Something you need to take into consideration when mining nuclear goodies like uranium or thorium.
If you've ever thought, what if I just dug a really, really deep hole? That's what the USSR.
Good luck making it to the Earth's core. 7,000 degrees Celsius heat and 3.5 million atmospheres of pressure. Makes nuclear power plants look mild.
Right here. That hole is deeper than the deepest part of the ocean. It's deeper than Mount Everest is tall.
Borehole.
They started digging it in the 1970s as part of basically a space race, but down. The United States.
I love this Cold War logic. Who can go further out into space or who can go deeper underground?
States only got to 600 feet before pulling funding, but the USSR kept going for 20 years. They made it about a third of the way through Earth's crust.
Which isn't that deep relative to the Earth, but that's a pretty impressive engineering feat, because at that depth, you're going to get temperatures over 300 degrees, which would exceed the capability of any drilling equipment. Not that many radiological hazards. I mean, you're going to have natural stuff like uranium-238, thorium-232, even some potassium-40, which is present in granite, but should be minimal unless it happens to be concentrated in the area you're digging.
And then stopped. But what if you just kept digging?
Deeper than that, huh? Well, temperature and pressure go way, way up. I want to say temperature goes up by something like 25 to 30 degrees per kilometer, and that's just the crust.
If you dug a hole all the way to the center of the Earth, what would you find?
Aliens. Okay, if you could somehow keep this hole open, because the extreme temperature and pressure, the Earth really doesn't like it when you do this. And hey, if you could go all the way through and come out the other side, and you somehow ignored heat, pressure, and air resistance, then yeah, it'll take you 42 minutes to fall all the way through, and you would just oscillate back and forth, up and down. But yeah, at that speed, you're gonna compress air in front of you into a plasma, so the whole ignore air resistance really isn't a good idea.
What would happen to you? And what does our newest tech tell us is really going on down below our feet?
Let's take a look at what's inside.
Journey to the center of the Earth.
Went where no human being had ever set foot.
Still falling!
The center of the
Oh my.
Earth, the heat and the pressure. What's underneath the Earth's crust is different.
The deeper you go into the Earth, the
I remember Magic School Bus when I was a kid.
hotter it gets.
That's wild.
The crust.
Imagine we go outside and we just start digging. At about 50 meters deep, we might start to feel the temperature go up.
Impressive speed.
Every kilometer through the crust is about 25 degrees Celsius hotter. Right now,
Yeah, now, initiating a deep earth borehole is a bit like starting up a nuclear reactor with no moderator, no coolant, no control rod. You might get it going, but if you were to keep going without any regards to limits of any of your materials involved, you're really not going to like what's going to happen. But at shallow depths, yep, everything still feels under control, just like a fresh reactor startup. Power levels low, temperature manageable, but unfortunately the Earth doesn't come with emergency shutdown systems built into it.
we're inside the crust. On land, it's typically less than 40 kilometers deep, which is less than the length of a marathon. We're passing through soil and layers of
Yes, a marathon going straight through rock. But even, I know this is kind of a silly thing, but trying to penetrate the crust all the way through the crust with mechanical drilling's a bit like trying to use a soda straw to bore through a 2-meter thick lead shield in your radiological controlled area. You're gonna melt your tools before you even see the other side due to said aforementioned temperature increase. Because heat and pressure will increase exponentially, just like neutron flux through a poorly shielded core.
hard rock past precious metals and fossils. And as we get deeper, we start to see all kinds of impressively deep things that people
You're gonna drill right next to an observatory.
have built. Like there's the Chemioka and Sanford research labs that do dark matter and neutrino physics research. Or there's China's insanely deep nuclear command bunker.
Yeah, I think that's adequate shielding from the events of nuclear war. You're probably going to get more radiation from the uranium or thorium deposits, and that's not even that much.
There's the deepest cave we've ever discovered, plus some of the deepest mines in the world. As we go deeper, temperature and pressure continue to rise.
You do have to mine uranium and thorium. It's one of the one of the more dirty sides of nuclear power generation, just because most forms of mining are not exactly known for being environmentally friendly, but you still come out ahead compared to mining stuff like coal.
But by this point,
and yes, renewables still have to mine some of their resources too. Silver, cadmium, materials used in solar panels, you still have to mine it.
unprotected, just in the earth, we were crushed and crispy a while ago.
Yeah. And even if you didn't send a person in here, you're gonna break your tools.
To go farther, let's equip ourselves with an imaginary drilling machine that's immune to any temperature or pressure.
Yes, it's coated in unobtainium, like in that movie The Core, which is incidentally also what they use in Avatar, but it functions differently.
Now, finally, at 12.2 kilometers, we reach the deepest point humans have ever dug. This is that hole the USSR dug, the Kola Super Deep Borehole. They didn't put any humans down here. This equipment was operated remotely. To get so deep, these scientists had to invent new equipment and drilling methods to pierce through the thick, hot, pressurized rock. Along the way, they discovered new fossilized organisms dating back 2 billion years, and found there was water, much deeper than scientists previously thought. We actually emailed 3 of the scientists who worked on this project, and one of them
And all in the efforts to just see who could dig the deepest.
told us, quote, "The Russians tried several times to get down past the maximum depth that they had reached, but each time, the new hole tended to collapse."
Yep, pressure goes up quite a bit. I want to say your pressure gradient is something like 2,500 to 3,000 atmospheres every 10 kilometers you go down, so...
This was a moonshot, which will never be repeated or surpassed. This
Probably easier to shoot the moon. I mean, I know that's an expression, but yeah.
is so cool. But the craziest part is, this deepest hole that humans have ever dug is only 0.2% of the way to the center of the Earth. Time to go deeper.
The mantle.
At about 30 to 50 kilometers down, we notice that the rock around us is changing. We're crossing into the mantle. At first, the rock around us looks really brittle, like the crust, but denser. But as we get a little deeper,
The details shown into this, each of the subsections. Yeah, here, I know this is a magical machine, but even if it was impervious, I wonder if, I don't think even a magical drill would work, because rock would tend to flow plastically under pressure, and let's face it, there's no realistic way to prevent hole collapse. Let's say magical force fields, tractor beams, stuff you see in shows like Star Wars. But yeah, you're in the, 500, 600, 700 degrees Celsius and going up.
as the temperature rises over
Okay, yeah, you're getting deeper.
1300 degrees Celsius, something weird starts to happen. The rock around us starts to look like hot plastic.
Yes.
Here, the temperature is higher than the melting point of the rock, but
So yeah, anything that's like a traditional drill isn't gonna work. I guess you could do some crazy Operation Plowshare type devices using focused nuclear explosions somehow, but again, I don't see how that's gonna prevent your hole from collapsing, but it can at least move this sort of stuff, provided said device can withstand temperature and pressure. Also, making a shaped charge out of a nuclear weapon, good luck with that. This sort of stuff reminds me of that movie, The China Syndrome, where they claim, molten nuclear fuel can go this deep underground. You're just gonna run into other molten stuff before you get to the other side of the Earth. Yeah.
the pressure is so high that it's still keeping the rock solid. It's gooey. We're now starting to push through even hotter material. It's slowly inching from the bottom of the mantle toward the top in these giant convection currents over millions of years. And you might be wondering, why is the Earth hot? Well, it's partly radiation and partly leftover heat from when the Earth formed.
Yep, nuclear decay is one of the things that we are quite grateful for giving us a planet. Also comes from the sun too. But yeah, she mentioned millions of years. This is a very slow convection process. So any realistic convection in the time frames of, hey, let's go ahead and go for a ride down to the center of the Earth in some sort of advanced super drill system. Yeah, in a narrow borehole, convection's virtually impossible on the scale that you would need, even if you disregard that thermal stress would obliterate all drilling tools at this point. Also, this could potentially create some localized microquakes because this area isn't particularly stable seismic-wise, which is one thing that we take into consideration when designing where to situate nuclear plants. are they seismically stable? So we don't put one directly on, say, the San Andreas fault line, and we certainly don't put one in the mantle. That somehow worked.
Meteorites smashing against each other over and over again. The Earth is cooling very, very slowly.
Convection is a very slow process when you're dealing with this sort of stuff.
But we don't need to worry about that. It's going to take billions of years. In the meantime, this stirring of hot goop brings enormous amounts of heat from the center toward the crust.
But yeah, this mantle, you're a high temperature, high pressure environment with no practical way to remove heat. Basically, you're causing a loss of coolant accident on purpose that typically results in fuel damage or meltdowns, except this is your goal in this particular design, is to get there. A self-escalating thermal feedback loop. Even if this magical device had self-healing capabilities, I'm not sure it would exceed the rate of heat being imparted on this device.
But hang on, how do we know that? If humans have only ever been 12 kilometers down, how do we know that?
Yeah, that's a great question.
That's Dr. Megan Newcomb, a geologist and volcanologist at the University of Maryland.
Volcanologist is a really cool sounding title.
She told me that studying the deep Earth is like being a detective.
We can't get there, so we have to put together
Indirectly.
all of these indirect pieces of evidence to work out what's going on down there.
Ancient scientists had a lot of theories about what was going on down there. Some thought the Earth contained a central fire with underground lakes and lava chambers. Some thought it was hollow, maybe a set of concentric shells with life on each ring. This is the basis for the hollow Earth in the Godzilla movies. Isaac Newton suggested that
Interesting.
based on observable gravity, the stuff in the center must be denser than the stuff at the top. But it wasn't until the early 20th century that scientists could prove that the Earth had a central core, and that there were several different layers above it. These breakthrough discoveries were thanks in large part to earthquakes. During an earthquake, we feel it up
Seismic
here, but
equipment.
it's also sending seismic waves down.
They are just like sound waves, but there are two main varieties.
This is kind of how neutron flux mapping or gamma scanning is used to map core geometry, because we don't want to send people in an operating nuclear reactor. You measure it indirectly, which is great. This is how we know about this stuff. You could theoretically use controlled underground explosions for a higher resolution of your seismic equipment. Kind of like how test reactors are typically pulsed in order to obtain diagnostic data. Pulsing the Earth.
There's P waves and S waves.
P waves can travel through liquids and solids, but S waves can only travel through solids. They also behave differently depending on the density of the rock that they're moving through, which means that by measuring what waves end up at different detectors all over the surface, scientists can understand what's going on between them.
Yep, that is exactly how neutron flux maps are performed. Now, you don't set off any sort of waves within the reactor, you're just measuring it, but it just generates a map based on where you place all of your detectors. And these are called in-core nuclear instrumentations. The X-core ones, the ones that you place outside of the core, are the ones that actually measure things like reactor power, overall reactor power. But one of many ways to do that. There's other ways to do that, such as measuring main turbine impulse pressure, heat balance equations for both the primary and secondary side of your steam cycle. But there's also in-core instrumentations that do a flux map and detect. They're designed to detect power peaking within the core, because ultimately in a perfect nuclear reactor would be a spherical core design where everything would be 100% uniform. But that's almost impossible to actually make. So in reality, you do what you can. You vary the enrichment on each of your fuel assemblies to try to produce a uniform heat profile and neutron flux profile the best you can. And you can get pretty close.
That's one big way that we've learned about how the mantle differs from the crust. And it also taught scientists something else.
We find this S-wave shadow on the opposite side of the planet that tells us that for some reason the S-waves couldn't propagate all the way through the Earth.
Yep, denser, thicker materials.
And that tells us that there's a liquid layer down there.
That liquid layer is part of what we now call the outer core. We've now crossed into a liquid soup of metals, cooking at around 4,400 degrees Celsius.
Yeah, we use liquid metals in nuclear power plants, but it isn't this hot. So breaching the outer core is a bit like breaching a sodium-cooled fast reactor's vessel with a garden hose. It's hot, it's reactive, and yeah, it's going to destroy your containment if you were dealing with anything less than whatever magical device this is. It's also magnetic. This liquid iron-nickel alloy is a magnetohydrodynamic fluid. That means if you're still using a regular drill, it's going to become a current-carrying conductor, and it's going to generate magnetic fields and localized heating. And yeah, this is the Earth we're talking about. No control systems are in place here.
Temperature has won the fight against pressure, and we should all be extremely grateful for the hot metal soup down there, because its constant churning generates enormous electric currents, which in turn create the magnetic field around the Earth. And
hey, it protects us from radiation.
Without that, cosmic radiation would just end all life as we know it on the surface. But this gets weirder. Our magnetic field sometimes actually just reverses.
Yep.
The North and South poles slowly swap places.
This happens every now and then, and if the swap was instantaneous, and really the most hazardous part about this is if it weakens, you're going to have increased radiation dose. So during these transitional periods is where you're at the most at risk.
And we know that because
you can actually read off all of those magnetic reversals on the ocean floor.
Yeah.
As basalt is erupted along our mid-ocean ridges, it freezes in a record of what the magnetic field was at that time. And as the plates continue to get created and pulled apart, we can read them off like a barcode.
So what you're telling me is there's a barcode for our magnetic fields at the bottom of the ocean, and scientists have learned to read it. Mm-hmm. Excellent. You can read this too. It flipped here, it flipped here, it flipped here. The last reversal was around 780,000 years ago. When will
that means we're due.
it flip next? We're not sure. But I had a much more basic question about all of this. Why is the Earth in layers?
You're gonna like this one. At the beginning, we were a magma ocean. The entire Earth was molten liquid. During that time, the densest materials, which are the iron metal, and sank and formed the core. And then the lightest minerals floated to the top, and the densest minerals settled to the bottom. And so we've segregated by density.
Okay, we've almost made it through all of those layers. We are deep inside the Earth's outer core. And then you hit something.
Okay, how magical is this thing if you made it through all this, but you couldn't make it through the inner core? So, yeah, 3.5 million atmospheres, temperature close to the sun's surface. I want to say we're getting close to the limit of material science, so nothing solid is making it here intact. But hey, this heat is driven by radioactive decay in the overlying mantle. Inner core.
At the very center of our planet, there is a solid metal ball that's almost as hot as the surface of the sun.
Not even remotely close to the sun's core, by the way. That's at 150 million degrees Celsius. That's at about 15 million Celsius, which is not that hot for a fusion reactor, but the sun has all that gravitational pressure that you can get away with a relatively low temperature compared to where you need 150 million or more on Earth. So no, the Earth is not a fusion reactor. What it is, though, is it's kind of like the center of a uranium dioxide fuel during peak burnup, superheated, under crushing pressure, and utterly inaccessible without destroying everything else to get there in the process. So there's not a temperature in a nuclear power plant for fuel centerline. It's all guessing based on what your reactor coolant system temperature is, which is on the order of 620 degrees Fahrenheit. Yes, I switched units, but the plant I worked at's in the US, so that's the number I committed to memory. But taking that, but what you do is kind of what they were talking about with seismology. You indirectly measure the fuel centerline temperature by taking reactor coolant system temperature, power peaking factors, neutron flux, and you just extrapolate based on that. Because no temperature probe is going to function at temperatures that high.
And for a long time, we didn't know it was there. We assumed that everything in the core was molten, because why would it be solid? But then, these two scientists were studying more of those seismic waves, and they noticed that when those waves got to the center, they started to act weird. Waves were being bent and reflected by something in the middle.
That's cool.
The math only made sense if there was a solid core inside the larger liquid one. Other scientists confirmed this theory, with more precise recordings of the waves and better computational models. minerals. So why is it solid? Well, it turns out that the pressure here is so insanely high that the iron atoms literally can't move. And what's even stranger is that more recently, scientists have found slight discrepancies in the data that seem to show Earth's core is rotating at a different rate than we are at the surface. And that rate changes. It is speeding up and slowing down separately from what we're doing up here.
That's fun.
Because why not? Very precise seismic data and computer models of our magnetic field show that the Earth's inner core seems to be speeding up and slowing down on a roughly 70-year cycle. You might have seen headlines that the Earth's core is reversing, but that's not true. It's just that if you were on the outside of the inner core and I'm on the surface, it would look to me like you were going the opposite direction if you're slowing down, even if we're both moving the same direction. But this iron core is no match for our magical digger. We are going straight through it.
Okay, so how would this thing even go? Even an antimatter tip drill with direct annihilation. I mean, good luck. Antimatter costs $100 billion a gram. You'd also have to, it would also require magnetic confinement, and anything that requires magnetic confinement wouldn't make it through the outer core due to said intense magnetic field sources. So that kind of rules out a fusion-powered plasma lance as well. And keep in mind, all of these things that I said are fringe technology that hasn't been developed. So I'm trying to see how you would do this, even stretching our understanding of nuclear technology. And anything using muons or neutrinos, well, there we're getting deeper into sci-fi tier technology.
Until finally, we did it. We made it to the
the center's this little red dot. That's cute.
very center. We are now 6,400 kilometers from the surface. The pressure around us is 3.6 million times what it is on the surface. But in lots of ways, what's around us right now is still a big mystery. Like, is there an inner core? Some scientists
Yeah, I was wondering what that little red thing was.
think that there might be. There's new seismic data that suggests that the iron atoms are packed differently
Just need to set off more bigger artificial earthquakes.
way on the inside, but others aren't so sure that that's enough to call it a new layer. We've been wrong before, but we're becoming better detectives. Can we predict the Earth's magnetic field and when it might flip? Scientists are building experiments that mimic the inner Earth to learn more. Now, the cutting edge is finding new ways to analyze seismic waves with better computational models and even finding ways to replicate the deep Earth conditions here on the surface. We are a curious...
That's cool. And this same technology, these optimization tools are also making flux mapping and heat mapping in nuclear reactor cores even better to make nuclear power that much more efficient and safe.
Species, locked on the outside of our own home, and we're doing everything we can to peek inside. That's what's so cool about science and technology. It lets us explore strange new worlds,
Using magic.
including the one right below your feet.
Yeah, I think Minecraft was more realistic than that drill. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.